Okay, in this item, what we've got is a gazebo, a really nice gazebo in someone's backyard, and the concern here is the seismic loading effect from a vertical standpoint, vertical accelerations. This is what's called a king post style arrangement for the truss. We have a truss on the front side and the back side in this gable arrangement. So we have a tributary load that comes into this particular roof plan. And if we were to model this in a computer, the way it's been constructed, we have a continuous top chord, continuous on both sides, and a continuous bottom chord, everything else being pin connected. And that's what's reflected in the computer model here. There's end A, C. At B, we got these web members that are coming in, these little circles indicating the release for that member, meaning it's pin connected. Right? So rigid joints otherwise. We've got this distributed load, that's the seismic load, acting vertically at 3/4 kip foot, and it acts along the incline here. Right? So let's check out dimensions. This is at 30 degrees, and we've got 7.5 feet here, 7.5 feet over there. How do I know all this? That's what we're given down here. That's what all this coordinate information is telling you. Right? So that's telling you those dimensions work out the angles here, and that's 30 degrees. That's why those heights are what they are. Right? Now the other thing that we're given here is the restraint that's provided by the nodes. Note at A, the X and the Y are fixed, but the rotation is free. In fact, all of the rotations are free on all of the nodes. And at C, then we're only fixed in the Y. So when you go look at the first task, which is to come up with a basic model associated with the supports, then we're going to come in and do a pin support at the left, because we're not allowing left and left-right versus in up-down movements or displacements, and we'll have a roller support at C, and that's what constrains movement in the vertical, but allows left-right movement. Right? So that's all there is to it for part A. And for part B, estimate the axial force caused by the seismic effects only in members BF and BC. Right? So now we got to go figure out what the loads are. These are vertical loads. They can be only applied at the joints. We don't really care about the load out here on the foundation itself. We do care for the columns that are supporting that, but we don't really care otherwise. This is going to be a tributary area calc to get these. Right? So let's go back to our where we're at. Right? 4 means we're going to come over to 2 here, and then over to between 4 and 7.5. So that's 3.5, and half of 3.5 is 1.75 here. That would be our distance. Oops. Did I say 2 plus the 1.75, or of course that equals 3.75 on the horizontal. Now on the incline, then we've got that length will be divided by cosine of 30, or 4.33 feet is what the tributary length is here. So let's call this P1, and P1 then would be equal to 0.75 kips per foot times our 4.33 feet. That equals 3.25 kips. And that's going to be the same by symmetry here on that one. And then the middle one, we're going to have, then that's going to be then from here to here, halfway over, that's 1.75 times 2. Oh, well, that takes us back to just 3.5. So the top load, call it P3, equals then 0.75 kips per foot times 3.5 feet, or 2.625 kips. Right now, I'm not including the load out here. Let's call that P4, P5. Those are the same. And so we don't really need them, but we'll feel better if we do it. Oh, hey, I made a slight mistake there. I didn't divide that 3.5 by cosine 30 degrees to get the right value. And whoops, didn't do something right. 2.625 by 30 cosine equals 3.03 kips. And then on the outer one we'll have then 0.75 times our 2-foot tributary divided by cosine of 30, and that will be 1.732, or square root of 3 for some interesting reason. And we don't really need that number. It's not going to help us any at all. Right? Why? Because it goes right into the support. So we need those two members. I'd say, hey, we can come and look at that joint right there. And so if we do that, we've got this member framing in. We've got that joint coming there, 3.25 kips. And we'll have compression in those two chord forces. Wow, that looks kind of intense, doesn't it? I don't really like that very well. That looks kind of hard to me. What if we did method of sections like that instead? If we did that was joint F, we got the reaction there. If we some moments about that reaction, I don't even need to know the reaction, I only need to deal with this little guy. And so why don't I come back to here and split that up into two little pieces. That's going to be kind of nice, right? So the y component of BF then is the only thing we have to deal with, and so we'll have 3.25 kips times the moment arm, which is, let's see, that was at 4 feet, and that has to be countered by BFY times this moment arm of 7.5 feet. And so 3.25 times 4 divided by 7.5, and then therefore BFY equals 1.733. Man, that's awfully doggone close to square root of 3. That's kind of interesting. Don't know why that would be the case. And then I got to figure out then its angle and all that kind of stuff. I don't really have to work that hard at this because we got a distance here that is 3.5 feet on the base, 2.31 high, and so the BFX then is going to be bigger. It's 3.5 over 2.31 times the 1.73. That equals 2.626, and then of course BF is the square root of the sum of the squares. So that would be 1.7333 squared plus 2.626 squared, and if I did that right, then that would be 3.14, or about pi, which is also a pretty bizarre number here. But let's, for a real structure that this was not planned out this way, 2.626 plus 1.773 squared, yeah, looks like that's about right, about 3.1 kips, and that would be in compression. That would be BF. Right? BC is going to be, I think, at some moments right over here at B. So this was some moments about C, some moments about B, well, that's not going to help us. That will get rid of the one we want. Don't do that. Instead, some moments about there, or we could come along and deal with this one. And so now what we got to do is we can't help it. We got to get R. No point in getting the 1.732 here. Let's just not do that. We got the 3.25 plus 3.03 divided by 2. That's half of that load. So we have a net of 4.765 acting up there. We've got then the chord force coming down here at joint F. That's CF. And so now what you end up with is the we're going to do a tangent business here, right? Because 4.7625, that's on this side, and that's opposite of the 30 degrees that I know is there. This is the one we want. So this is BC. And so now BC is going to be equal to, see, opposite over this is equal to tangent, so we want that. It'll be then 4.765 divided by tangent of 30 degrees. And that makes BC equal to 8.25 kips in tension. Right? Just to summarize that real fast, our answers were BF equals 3.1 kips in compression and BC equals 8.25 kips in tension. There's your answers.